Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Debye theory of specific heat in solids. Let's begin. We have already discussed about DeLong and Petty's law and Einstein's theory of specific heats in solid. In case of DeLong and Petty's law, we saw that the specific heat in solids is a constant, means Cv is equal to 3R at high temperature, but it can't explain at low temperatures. And totally that DeLong and Petty's law is based upon the classical theory. Such drawbacks can be overcome by Einstein's theory of specific heats in solid. According to Einstein, he proposed the quantum theory and he saw Cv is equal to 3R, means specific heats at constant volume is a constant at high temperature, and at low temperature it is directly proportional to just like a term having exponential something, but actually that is deviate from the experimental result. In experimental result, the specific heat at constant volume is directly proportional to the cube of absolute temperature at low temperature situations. So, the quantum theory as proposed by Einstein to the specific heat in solid is again a limitation. To avoid such kind of limitations, a new theory is proposed by Debye, and that particular theory is based upon the idea of phonons. Phonons is nothing but the quantization of lattice energy. As we say, in case of electromagnetic waves, the quantization of electromagnetic waves is known as photon. In the same way, the quantization of lattice energy is known as phonons. And by using that phonon theory, Debye show the specific heats in solid at low temperature as well as at high temperature. So, let me discuss what are the assumptions proposed by Debye to show the specific heats in solid. Assumptions: solid is treated as anisotropic continuous elastic media in which the motion of each atom is influenced by its neighbor atoms. Next point, solid is non-dispersive. Non-dispersive in the sense the velocity of sound is not depend on the frequency. Next point, solid vibrates as a whole, having frequency range, that frequency range from acoustic to infrared regions. Acoustic, the frequency of sound. The internal energy of the crystal is due to the vibrations of individual atoms present in that of elastic stationary waves that are caused by the vibrations of individual atoms. Next point, the energy of elastic stationary waves is quantized, and a quantum of vibrational energy which is known as phonon, that has energy h nu. H is the Planck's constant, nu be the frequency, which is similar to that of photon. Nu is the frequency of vibrations. These are some kind of assumptions proposed by Debye to show the specific heats in solid. Let me derive the specific heat in solid by using that phonon theory. First of all, Let us consider a unit volume of continuous solid. That solid is subjected to elastic vibrations. In case of elastic vibrations, there are two kinds of elastic vibrations. One is longitudinal vibration, another one is transverse vibrations. Let we take longitudinal vibrations with the speed of CL, speed of longitudinal vibrations, and the speed of transverse vibration is CT, speed of transverse vibrations. And again, the number of longitudinal modes of vibration per unit volume in that of frequency range nu to nu plus d nu, the number of longitudinal modes will be 4 pi nu square d nu divided by its velocity CL q. That is the number of longitudinal modes of vibrations per unit volume within that of frequency range. Next, what will be the number of transverse vibrations per unit volume in that of given frequency range? In case of transverse vibrations that are polarized in two perpendicular directions, therefore, the number of transverse vibrational mode per unit volume in that of frequency range nu to nu plus d nu is given by, that is 2 times. So, 2 into that quantity, it will be 8 pi nu square d nu divided by its velocity q, Ct q. So, what will be the total number of independent modes of vibrations? Therefore, the total number of independent mode of vibrations in the given range of frequency nu to nu plus d nu in that of volume V, we denote it as f nu d nu. We add these two modes, that is 4 pi nu square d nu divided by CLQ plus 8 pi nu square d nu divided by CTQ. In these two terms, 4 pi V as common. In that of bracket, we have 1 by CLQ plus 2 divided by CTQ nu square d nu. Here 2 is multiplied as it is polarized in two directions. Next, this is the total number of independent modes of vibrations within that of frequency range. Since the total number of independent modes of vibration is equal to the total number of degrees of freedom of all atoms in that of solid, total number of degrees of freedom of all atoms in the solid, which is 3n, 3 with the number of degrees of freedom, n with the total atoms present in that of solid, and that must be within that of upper limit of frequency. Therefore, 3n is equal to total number of independent modes of vibration, that is f nu d nu, f nu d nu within that of maximum frequency range 0 to nu m, the maximum frequency range. Now, putting the value of f nu d nu as 4 pi V 1 divided by CLQ plus 2 divided by CTQ nu square d nu, that will be the constant term to outside 4 pi V 1 by CLQ plus 2 divided by CTQ. In that of integration, it will be nu square d nu from the limit 0 to nu m, that is the maximum frequency range. Its differentiation nu q divided by 3 upper limit nu m to that of lower limit 0. So, that integral result as 1 by 3 nu q m, that 3 is multiplied to this side. So, 9n divided by nu m q is equal to 4 pi V 1 divided by CLQ plus 2 divided by CTQ. Look at that equation number 1 and equation number 2. From equation 1 and equation 2, we get, so instead of f nu d nu that represent the total number of modes of vibrations within that of frequency range nu to nu plus d nu, that is f nu d nu is equal to, instead of this term we use 9n divided by nu m q. In that term we write 9n divided by nu m q nu square d nu. According to quantum theory, the energy associated with each degree of freedom is the energy of a Planck's oscillator, that is h nu divided by e to the power h nu by k t minus 1, k that is the Boltzmann's constant, the energy of each quantum oscillator. Then what be the total internal energy? Therefore, the total internal energy of the solid is given by total internal energy U is equal to, that is integration from the maximum frequency range 0 to mu m n nu d nu. So, what is n nu d nu? That is nothing but the product of energy of one oscillator to that of total number of mode of vibrations, that is equal to zero to nu m f nu d nu into energy of one oscillator, that is h nu divided by e to the power h nu by k t minus 1. Now, putting that value, integration of nu m 9n nu square divided by nu m q nu square d nu. So, h nu divided by e to the power h nu by k t minus 1 d nu is equal to 9n divided by nu m q, constant term to that of outside, 0 to nu m h nu q divided by e to the power h nu divided by k t minus 1 d nu, that is for u total energy. Now, we can calculate specific it from that of total energy concept. We know that Cv is equal to du by dt at constant volume. Let me differentiate it with respect to t at constant volume. Is equal to 9n nu m q integration from 0 to nu m h nu q d by dt of 1 divided by e to the power h nu by kt minus 1 d nu is equal to 9n divided by nu m q integration from 0 to nu m h nu q. That differentiation also we write as partial differentiation, differentiate only one variable. It is written as del 1 by e to the power h nu by kt minus 1 del t d nu is equal to 9n divided by nu m q integration from 0 to nu m h nu q. Its partial differentiation as e to the power h nu by kt into h nu divided by kt square whole divided by e to the power h nu by kt minus 1 whole square d nu is equal to 9n divided by nu m q integration from 0 to nu m it is h square k t square nu fourth e to the power h nu by kt divided by e to the power h nu by kt minus 1 d nu. Okay. Next 9n divided by nu m q h square divided by k t square integration from 0 to nu m nu fourth e to the power h nu by kt divided by e to the power h nu by kt minus 1 d nu. Here we have a substitution. Here we have a substitution as h nu m by k is equal to theta d, which is known as the Debye temperature, and let we substitute x is equal to h nu by kt, and therefore its maximum value x m is equal to s nu m kt, s nu m by k, that is theta d, so theta d by t. These substitutions are used. Therefore that equation can be written as 9n divided by nu m q h square divided by kt square, here integration from 0 to xm kt by h into x to the power 4th into e to the power x divided by e to the power x minus 1 here whole square kt by h dx is equal to 9n divided by nu m q h square divided by kt square k to the power 3 t q divided by h q nu mq integration over 0 to xm x to the power 4th e to the power x divided by e to the power x minus 1 whole square dx. Here h square by kt square k to the power 5 t to the power 5 h to the power 5. Okay, next simplifying it, we have 9 n k into n its cancellation as kq tq divided by hq nu mq in integration 0 to xm x to the power 4th e to the power x divided by e to the power x minus 1 square dx is equal to 9nk. These substitutions are used, so t by theta d whole cube integration from 0 to xm x to the power 4th e to the power x divided by e to the power x minus 1 whole square dx, that is equal to Cv. That is equation number 3. Now we can derive what be the specific heat of solid at low temperature and high temperature by taking that equation. Case number 1, at high temperature, so theta d by t is very less than 1 and x very less than 1, therefore e to the power x is nearly equal to 1, therefore e to the power x minus 1 is nearly equal to x. So that equation number 3 becomes, so equation number 3 becomes Cv is equal to 9nk t by theta d whole cube integration from 0 to theta d by t, that is x fourth into 1 divided by x square dx, as e to the power x minus 1 is equal to x and e to the power x nearly equal to 1. 9nk t by theta d whole cube integration from 0 to theta d by t, that is x cube dx, so 9nk t by theta d, that will be x fourth by 4th, limit from, okay, that is x square dx, it will be x cube by 3 0 to theta d by t, using upper limit and lower limit that 3 is divided here, it will be 9nk T by theta d into theta d by T whole cube, that is the cube. These two terms are cancelled out each other, so it will be 3 nk, as nk is equal to R, therefore Cv is equal to R at high temperature. Therefore at a high temperature, that theory result almost same as that experimental result. Next, at low temperature, case number 2, at low temperature. At low temperature, the value of theta d by T is greater, very greater than that of 1, therefore x is very greater than that of 1, therefore the maximum value of xm, which is theta d by T, tends to infinity. So equation number 3 becomes Cv is equal to 9nk T by theta d whole cube, and that integration from 0 to infinity x cube dx divided by ex minus 1. That standard integral value is nothing but 9nk T by theta d cube. The standard integral value is pi to the power 4th by 15. Look at this equation. In all these terms, n, k, theta d to the power cube, 15 pi to the power 4th, all are constant. So Cv is directly proportional to Tq. This is known as Debye Tq law, and that is same as that of experimental result. And when we plot the graph between Cv and T by theta d at 3R, we obtain from that of experiment. So the graph is looking like this. That graph for Einstein's and that graph for Debye. Now by using Debye theory, we show that is almost same to that of theoretical, that is almost same to that of practical result at a high temperature, at low temperatures. So here, with the help of this video lecture, you understand the concept of Debye theory of specific heats in solid, some assumptions regarding this, then derivation of that specific heats in solid, total energy is calculated. By using total energy, we evaluate the specific heat at constant volume. That equation shows that specific heat at constant volume. Next, at a high temperature, Cv is equal to R. At low temperature, it is directly proportional to that of cube of temperature. It is almost same to that of experimental results. The graphical view that showed from Einstein's theory of specific heat in solid, that graph shown by Debye. So with this useful uninformative notes, let me wind up this session. Thank you.